Hi everyone, welcome to Ong Learning Lab. In this video, we are going to solve best time to buy and sell stock 3. Now before solving this problem, I would highly recommend people to go back and watch the solutions to best time to buy and sell stock versions 1 and 2, as they are based on similar ideas which can be helpful in this version of the problem as well. I have attached the links to those videos in the description of this video. Without any further ado, let's get to this particular problem. So the problem states that you are given an array prices where prices of I is the price of a given stock in the ith day, exactly same as the first two versions of the problem. Find the maximum profit you can achieve. You may complete at most 2 transactions. So if anyone remembers, in the first version, we were allowed to do just 1 transaction. It was an easy problem. In the second version, we are allowed any number of transactions. And in the third version, they are saying we are allowed at most 2 transactions. And this is the condition that they have given, additional condition, that we cannot engage in multiple transactions. That is, we have to sell a stock before we buy. We cannot do 2 sales, or we cannot do 2 purchases simultaneously, so to speak. Keeping that in mind, we can take a look at the examples and try to figure out an approach. So for this particular example, they are saying that the output is 6, we will buy on day number 4, price is 0, sell on day number 6 for price 3, and we get a profit of 3. Then we buy on the next day and sell on the final day, we get another profit of 3. So the total profit is 6. Now, usually, whenever problems involve, numbers of 2, so here we have at most 2 transactions. And what's more, this problem is based on the idea of buying or not buying. So for any particular day, let me take this example, 335,003,14. Let's go to our notepad. So you can choose any random example, actually it doesn't matter. So it is something like 005, whatever, it doesn't matter. 103, let's just take some example, 1, 2, whatever. And we are allowed to do 2 transactions. Now, as I was saying before, whenever any problem involves numbers 2, like we are allowed to do 2 transactions, or it involves something like either you do or you don't. So for any particular index, you are at, either you buy or you don't buy or you don't. Similarly, either you sell or you don't sell. That's all you have to do, right? You have to do 2 transactions at most, and every transaction is basically a buy followed by a sell. So we have 2 purchases and 2 sells at most. Now, whenever you have terms like this, ideas like this, it's usually a good idea to see if binary state DP fits the criteria or is able to solve the problem. So I am talking about binary state DP here. It's a well-known paradigm, binary state DP, but basically every DP state, DP of I will have, DP of I is basically what is the, how does the array look like at the ith index, has 2 states, 0 or 1, or we have DP of I at 1. So there are 2 states. Now, as it is the case with all DP problems, the most important part is defining the state of DP array, how a particular state will look like. For this particular problem, I am going to keep it extremely simple. So I'll define DP of I, J and K as DP of I, J and K. So this DP signifies the maximum profit I have got, obviously, in the given array. And what does this signify? I is the index. So the current index I am at, let me use a different color for this notation. Let me use blue. So I represents the index that I am at. J, it can be either 0 or 1. And 0 means I am doing the first transaction. So there are 2 transactions involved. So J is 0. It means I am correctly doing the first transaction. 1 means I am doing the second transaction. So there are two transactions involved. So I am putting that into my DP array. That is one of the states. The third state is, again, this k can also be 0 or 1. And that will represent either I do the transaction or I don't do the transaction. Like it is either buy or sell. So if it is 0, I'll represent it as buy. I am doing a buy. 1 means I am doing a sell. So apologies for an error that I did a few seconds back. The state does not represent it is buy or don't buy or sell or don't sell. For this particular solution, I have kept it as either you do a buy type of transaction or you do a sell type of transaction. Now, whether you actually buy or you don't buy and you sell or you don't sell, that will do through code. So code will take care of that. So these things, either you don't do a buy or you don't do a sell, that will be handled through the code. But for the states, this is how I have defined the states. I is the index I am at. J can be 0 or 1. 0 means I am currently doing the first transaction. 2 means it is the second transaction. K can also be 0 or 1. 0 means I am doing the buy. 1 means I am doing the sell. Now, how do I build a relation out of this? So what I can do is, so let's say for any particular state, let's say it's something like dp of I 0, 0. So for any index, I'll have 4 things basically, right? So I'll have dp of, let me scroll here. So I'll have 4 states, dp of I 0, 0, dp of I 0, 1, dp of I 1, 0, and dp of I 1, 1. What does this signify? It means that at the ith index, if I am doing the first transaction and it is a buy type of transaction, what am I going to do? Similarly, at the ith index, if it is the first transaction and it is a sell type of transaction, what am I going to do? And so on and so forth. How do I define this? What you can do is, if it is the first transaction and it is a buy type of transaction, I am doing the first purchase, what can it be? Either I am buying at that particular index, like whatever stock I have at index number I will buy it. If I buy the stock that is at index number I, that is the first transaction, what will be the net profit? It will go to negative, right? I mean, I am buying something, I am spending something. So the net profit goes to negative and there is no transaction done before. So either I can buy there, which will be negative of prices of I, right? Because this is the first transaction that I'm doing and it is a buy type of transaction. So I'm spending something. So either it is that, or there is a better choice that I have encountered before, which will be dp of I minus 1. I mean, of course, since we keep on optimizing states of dp at each step, I can safely assume that dp of I minus 1 will have the most optimal possible arrangement till that state. So either I buy at I or I just take I minus 1 state 0, 0. First transaction at I minus 1 state and it is a buy type of transaction. Whatever was optimal for I minus 1, either I take that or I actually bought at index number I and I'll take the max of it. So here is where we are implementing the idea of buy or don't buy. So this is my buy condition. If I buy, I'm spending this much. Or if I don't buy, I will take something from the previous states. That is dp of I minus 1. Now one may think that what is the guarantee that dp of I minus 1 has the most optimal solution for the first transaction, which is a buy type? Because it is optimal, because again, it would be the same thing, right? It would be either minus of prices of I minus 1 or the previous state and so on and so forth. So we are sure that the most optimal solution is there. This is for first transaction buy. Similarly, for first transaction sell, either we sell at the current location. For that, what will happen is prices of I will be in positive. But since we are selling in the previous state, for the first transaction, we must have done a buy. Just a second, let me fix it. Apologies. So in the previous state at I minus 1 for the first transaction, we have done the purchase, the most optimal purchase, and then we are selling. Either this is a choice, we are selling at index number I for the first transaction, or we can take the most optimal choice for the previous state. As usual, dp of I minus 1 for the first transaction for a sell. And again, max of both. Again, through this max, we are implementing the idea of sell or don't sell. This is sell or don't sell implementation right here for the first transaction. I'll repeat it once again what I did. So either I buy at prices of I. If I do that, I'll look at what was the most, either I sell at prices of I. In that case, prices of I will be added because I'm getting something. And it will be added to the previous DP states buy. Right? So first transaction buy, the most optimal choice has to be in DP of I minus 1. That's how we are defining our DP states. So that optimal buy plus the current sell. Either that or you just take a sell from the previous state. That is for the first transaction. Now defining second transactions, like when you are doing the second transaction, is relatively easier. So it will be either you would do a buy at the current state. Now please be careful here. If I am doing a buy for the second transaction, that means I must have done a sell for the first transaction, which means it is dp of I minus 1, 0, first transaction, 1, sell. I have sold for the first transaction, minus prices of I. I am buying for the current transaction. Either you do that, or as usual, you don't buy at index number I for the second transaction. That means you must have bought it earlier. So dp of I minus 1 for the second transaction, you have done a buy somewhere earlier. You have two choices. The final dp state, either we do a sell at the current position, prices of I will be added, but it will be added to a buy for the second transaction. So dp of I minus 1, second transaction, buy. Okay? I mean, that's the benefit of using binary state DPs. You don't have to think a lot. You just intuitively know what is it that you are going to do, what is it that needs to be done in the problem, and you just translate it into code. That's what I'm doing here. This is the second transaction sell. So either I'm selling here, and if I'm selling here, I must have done a buy before for the second transaction. So this is previous state, but second transaction is 1 and buy is 0. That's it. Or you just pick a second transaction sell from the previous state, the most optimal one. dp of I minus 1, second transaction, and sell. That's it. That's how we can define the states of the DP for this particular problem. And we can solve this problem easily. Of course, we have to take the most optimal among all these states. In fact, intuitively, one can understand that one of the most optimal states is always going to happen when you do a sell. I mean, when you are doing a buy, you are incurring a loss. When you are doing a sell, you are getting something positive. Of course, one of the sell states will be most optimal. That is the states which have the ending with 1. So one of these states among all the i's, when we iterate from 0 to n minus 1, will be the most optimal. So just keep updating some variable and then return it as your answer. That's it. So this is how it's basically using bottom-up DP, so to speak. We'll iteratively build our DP states from scratch to up. We'll define our base cases first and then keep on building our DP array using these recurrence relations. And we'll keep on updating our answer and returning it. I'll go through the solution once again and then I'll go through the code. So we started off by saying that we have binary states. That is, we can at most perform 2 transactions. So that I denote by J for first and second transaction. Then we can do either a buy or sell, that I represent as K. So for every state, we'll have 0, 0, 0, 1, 1, 0, 1, 1. 0, 0 meaning it is the first transaction buy. 0, 1 meaning it's the first transaction sell. 1, 0 meaning it is the second transaction buy. 1, 1 meaning it is the second transaction sell. And then we keep on defining these states. So for example, if it is the first transaction, purchase, either you purchase at I, in which case you will incur this particular loss, or you can take the optimal state from a previous state. So buy or don't buy is implemented here. Similarly, if it is first transaction sell, either you sell here and that sell price will be added to a previous buy price for the first transaction, or you take a sell for the first transaction from a previous state. Similarly, the remaining two states are also defined. That is, if it is the first transaction buy, either you buy at the given index, and since you are buying for the second transaction, first transaction sell must have been completed. That is being ensured by this particular condition. Please pay additional attention here that by doing this, we are enforcing that when we are doing a second transaction purchase, second transaction buy, you must have finished the first transaction sell. So either that or you just pick another one of the previous states which is most optimal for the second transaction buy. Similarly, the final state is second transaction sell. Either you sell at I and you will sell after having done a buy for the second transaction in some previous state, which is this, or you directly pick one of the previous states. That's it for the explanation of the problem. Binary states and correct definition of a TP always makes the problem much simpler. Now let's go through the code quickly. So I had hidden the code knowingly because it was already present. Let's go through the code. So what I'm doing here is this is just defining n, which is the size of the array, pretty standard. If n is 1, return 0. I mean, if there is just one element, you can buy and sell there, you will not get any profit. Then I have defined the DP array, which is the 3D array. In the explanation, also we used a 3D type of array. First state is the total number of elements, the current index, so it will be n, and the rest will be 2 sized. So that's what I have done here. Then this is important to understand. I have initialized all the buy states, like maybe it is the first transaction or maybe it is the second transaction. But if we are buying something, I have defined the buy states as I have initialized them as int min to ensure that transactions happen. Because since I am taking the purchases as negative, if I initialize them with 0, let's say, transactions will never happen, right? If I take max of something negative and 0, it will be 0. So ultimately we will be returning 0. There will be no transactions at all. So buy states have been defined as int minimum so that whatever negative value we are getting are actually bigger and transactions start happening. That's why this definition is important. And then I have done some base value initialization, like the initial answer I have defined as int min. Of course, we'll keep on updating that. It is a standard practice. And DP of 0, 0, 0, that is the first index. I am doing a buy for the first transaction. So that has to be negative of prices of 0, because if it is not, then it is int min, right? So it is by default the optimal choice. If I am at the first index for the first transaction and doing a buy, it is always optimal to do a buy there, because there is no previous option. There is no TP of I minus 1 there. And if I don't do a buy, int min is always highly negative. So the most optimal choice there will be to buy it. That's the only option I have, in other words. That's it. So that is the initialization that I do. This is the only option basically. And then I just do the DP looping. If you pay attention, this is exactly what I discussed in the notebook. These are the states. This is exactly what I am doing here. Define the 0, 0 state, define the 0, 1 state, define 1, 0, define 1, 1, and keep taking the max of the states which have ones at the end. That is, they are cell states. Intuitively, obviously, they have to be most optimal. And that's it for the solution. If I submit it, it will get submitted and we are through. We can quickly look at the time complexity and the space complexity as well for both of this. So time complexity will be, since we are just literally just iterating through the entire array and doing on updates, we are not looking at further states, we are just looking at the previous state. So it is linear. So time complexity will be big O of n, which is linear time complexity. And when you have an array involved and n elements involved, this is really the best you can do of n. I mean, depends on the problem. Sometimes it can be logarithmic, but for this particular problem, this is the best we can do, linear time complexity. And space complexity is we are using additional space. And since it is a 3D array, it might look like we are using a lot of space, but that's the beauty of binary states. It's not a lot of space. So it's basically big O of n multiplied with 2 multiplied with 2. For every of the n elements, we have 2 states, which is for first or second transaction. And we have further 2 states, which is for buy or sell. So it is big O of 4n. And in fact, in big O notation, that's same as big O of n. So this is the space complexity involved. So that's it for this video. I hope you got some idea, got some intuition regarding how we can use binary state DP for this problem and actually appreciate the beauty of the concept, the application of the concept. So I'll see you in the next video, which is the 4th version of the problem and the hardest version of this particular problem. We'll solve it using another DP technique. Spoiler alert. See you there. Thank you for watching the video.